Here we have a differential equation with non-constant coefficient on one of the terms, and that's supposed to be a y prime there. I'll be sure and correct that for you. And we want to, assuming that this is our solution, a power series solution, we want to show that we can get this relationship. And so that comes from taking our derivative, which is going to be sum n equal 1 to infinity, n an x to the n minus 1, and taking our second derivative, it's going to give us the sum n equal 2 to infinity, n minus 1, a sub n x to the n minus 2. So I'll plug those in here. Here's the second derivative, sum n equal 2 to infinity, n minus 1, a sub n x to the n minus 2, and then x times the derivative, that's sum n equal 1 to infinity, n a sub n x to the n minus 1, and then 2 times y, which is n equals 0 to infinity, a sub n x to the n, and that's supposed to equal 0. So now we just go through our standard steps. First, I'm going to take these things that are outside the series to the inside. So here's n equal 2 to infinity. This one doesn't have anything on the outside, so I'll leave it alone for now. And I get that, and then bringing this x in, it bumps that power up by 1, so I get sum n equal 1 to infinity, n a sub n x to the n, and then the 2 goes inside that one. N equals 0 to infinity, 2a sub n x to the n. Next, now that I've got everything inside, I want all my powers on my x's the same in each of the power series. So this one, I'm going to, since I've already got n on those, I'm going to take m and replace n minus 2 by that, which is the same as saying n is m plus 2. And so this series is going to become m equal, well, when n starts at 2, m is going to start at 0. And then I have n, which is m plus 2. And then I have one less than that, which is m plus 1. And I have a sub n, which is m plus 2. And x now is to the m power. And then these next two are still going to be the same. I'm just going to not rewrite the whole thing. But I will rewrite it now, putting n in this place. So I have n equals 0 to infinity, n plus 2, n plus 1, a sub n plus 2, x to the n. And then I have this one, which is n equal 1 to infinity, n a sub n x to the n. And this one, which is n equals 0 to infinity, 2a sub n x to the n equals 0. And I know what I need to do next is start these all out at 1. So I need to sum off the first one here. Well, let's see, when I put in 0, I get 2 times 1, a sub 2. And I'll still have the rest of these, which is starting at 1 now. So I'll just rewrite the power series. Here I don't sum any off because it's already at the starting value that I'm trying to get the other ones to. And then here I have to sum off the first one to get 2a0. That's plugging in the 0, x to the 0 on that. And then I have sum plus the sum. Now it starts at 1, 2a sub n x to the n. And so if I take these two out in front, I've got 2a2 plus 2a0 plus each of these sums. I'll write them down real quick. N plus 2, n plus 1, and then we have a sub n plus 2 x to the n. And I'm going to factor that x to the n out of the rest of these. So keep it, take that one, and then I have an n plus n a sub n from this one, take out the x to the n, and then I have 2 a sub n from this one, and there's your x to the n. And that hopefully looks like what we were asked to show. 2a2 plus 2a0, yeah. And then all of these, there they are, with the x to the n pulled out. And then as a last step, down here it says, given a0 is 1 and a1 is minus 1, find the values of a2, 3, 4, 5, 6. Well, the way I'll do that is from here, I know that 2a2 plus 2a0 has to be 0. That is, a2 is the opposite of a0 when you solve that. And then I get my recurrence relation. So let's see, from in here I know that these two are going to combine to give me n plus 2 times an. So here's what I have. I have n plus 2, n plus 1, a sub n plus 2 plus n plus 2 an has to be 0. And that's for the rest of the n's, 1, 2, 3, etc. I can solve this to say that a sub n plus 2 is going to equal, I'm going to bring that to the other side, so I have minus n plus 2 times a n, and then divided by this coefficient on the a sub n plus 2, so that's n plus 2, n plus 1. So it's minus an over n plus 1, and again that's for 1, 2, 3, etc. Okay, so I'm given a0 is 1, so I can already get a2, so I need to find a2. That's going to be minus 1. I need to find a3, a4, a5, a6. But I'll get those from this relationship. So from here I can see that a3, when n equal 1, I get a3 equals minus a1 over 2. But we're given a1 is minus 1, so that's going to be minus a minus 1 over 2, which is going to be positive 1/2. So there's a3. And then when n is 2, I get that a4 equals minus a2 over 3. But I already know a2 from up here, so this is going to be minus a minus 1 over 3, so I get 1/3. And then we'll do a5. a5 from my recurrence relation, that's when I put in n equal 3. When n is 3, I get a5 equals minus a3 over 4. But a3 is 1/2, so I get, go ahead and take that minus 1/4, and a3 is 1/2, so I get minus 1/8. And the last one, when n is 4, I get a6 is minus a4 over 5. But a4 is, so I get minus 1/5. a4 is 1/3. So I get minus 1/15. Hopefully I didn't make any arithmetic errors, but anyway, those are the coefficients. And I could then create the polynomial. So what I would have, the starting values would be the constant term, minus 1 times x, and then this is my coefficient on x squared, this is my coefficient on x cubed, and so on. Next one would be x to the 4th. That's positive, sorry. And then x to the 5th, and so on. And this would keep going infinitely, but this would be a good approximation to the solution if you wanted to graph that or whatever. But obviously you couldn't do that on the exam.